which was a mathematical way to explain diffusion from Unit 2. As you can see, there's no image of me on this one because I got it right on my screen, so I can't write on the screen and use the camera at the same time. So we'll just go through it. Water potential has to do with the ability for the water molecules to move. Remember, all molecules are always moving around, and so they all have the potential to move. The more water molecules there are, the higher the water potential, and that's the basic idea. But what it really comes down to is not the water. As always, it's about the solute. It's the stuff that's in the water that's going to make the difference. And so the idea is that higher amounts of solute result in a lower water potential. More solute means the water can't move as much. That's because when you dissolve things in water, the water molecules are attracted to, in this case, the sodium or chlorine ions, and they make something called a hydration shell, where all the water molecules are stuck around the outside of the ions. And that means that all these water molecules that are stuck to the ions can't move anymore. They're not free to move because they're stuck. And so the more solutes you have, the more hydration shells you'll need to make, and the more water molecules will be stuck and they won't be able to move. And so that makes the water potential go down. Now, you can make it go up by adding pressure. This is more of a physics situation. We're probably not going to have to deal with it too much. It is a problem with plants. Since the plants have a cell wall, they can actually increase pressure in their cells. Animal cells don't have a cell wall, so you can't really add any pressure to it. And most of the time, you're going to get animal cell questions, although there will be sometimes maybe it'll come up. So just make sure that you realize that. And so pure water has a water potential of 0 if it's in an open container. That's the highest possible water potential. Everything else will be negative, which again, if you remember, that's going to be an issue, remembering that we're dealing with negatives a lot. As always, water moves from areas of high water potential to low water potential. Again, that just is a fancy way of saying from high concentration of water towards low concentration of water, which is exactly what diffusion and osmosis has always been about. So the main formula looks like this. That symbol is called psi, but the water potential is broken into 2 parts. The pressure potential, which again has to do with the pressure, and like I mentioned already, open containers in animal cells have a pressure potential of 0. The only time you would have any pressure would be in a plant cell, and I haven't seen too many of those on the AP exam, at least. But there's a lot of open containers, so that's a big deal. The solute potential is the bigger part of it. Solute potential has its own formula, negative I CRT, and so then we need to know all these different variables. I, for the ionization constant, how much solute will there be? When you put salt in water, it breaks into 2 pieces. It would have an ionization constant of 2. But glucose, when you put that in water, each glucose molecule does not split into any smaller parts, and so that would have an ionization constant of 1. Most of the time that will be given to you, but you should know things like the salt and the glucose, because those are the 2 most common things to be talking about. C, the molar concentration, because of course the concentration of solute is important. The pressure constant, R, is always going to be 0.0831. The liter bars over mole kelvins, this is an important units. That will be a good road mark for us when you're going through to make sure that all of these variables have the right units. If you ever see an R that isn't in liter bars, moles, kelvins, then that tells you that some sort of conversion is going to have to be done, because we always need it to be liters, bars, moles, kelvins. Finally, temperature is in Kelvin, so that's Celsius plus 273, right? And so let's just jump into some of these practice problems, starting from the simplest to the most difficult. Here we have an idea of a cell with these different components to its water potential. We want to know the actual water potential. So we start with our formula, and then we try to fill in what we know. In this case, we know a lot of things. And so we end up just doing some math. So we know that by adding the pressure potential and solute potential, we end up with an overall water potential of negative 1.5. Again, keeping track of your signs is going to be important. So then we take that cell and place it in a beaker of sugar water, and I immediately draw my beaker that has a solute potential of a certain bars, -4 bars, right? So I set up my situation looking like this. I have my beaker with my cell. I always go in here and just put my formulas because this is where everything comes from. And then I go and I try to figure out, what do I already know? And so I already know that the solute potential here is -4 bars, right? I also know that this is 0 because it's in an open container. So now I know that the overall water potential is -4 out here in the solution. Inside the cell, we have our formula, although we just figured out in question 1 that the cell has a water potential of -1.5 bars. So the final question is, which direction will the water flow? And so water is always going to go from high to low, from high water potential to low water potential. -1.5 is bigger than -4. And that's a hard one, right? You look at the 4, you look at the 1.5, and maybe you naturally think it goes into the cell. But in this case, the water should be flowing out of the cell and into the solution. All right, so then now we're going to take the original cell from question 1 and put it in a beaker of sugar water. But this time the sugar water has a solute potential of -0.15 megapascals, right? And so here's the situation of where we need that to be in bars, right? That's not going to help us. And so in this case, this is just trying to get us to remember that conversions could be a thing. And the conversions are always the same way. A fancy way of this is called dimensional analysis. But I know that I have the starting of -1.5 MPa, but I don't want it to be an MPa anymore. So I'm going to do a multiplication times this ratio. I want MPa to go away, so that goes on the bottom. I want bars to be on the top because when I do this math problem, those will cancel out. And so we have 10 bars for every 1 MPa because that's what just told us to in the question. And so now I know that the, oops, it's not a 0, it's a -1.5 bars, right? Now, I know that out here, it's -1.5 bars, and from question 1, it's 1.5 bars. So this is going to mean that the water is going to go in both directions at once, which would be a net flow of 0, right? This is an isotonic situation, equilibrium. Right, so that's just a reminder that you might have to do conversions here and there. All right, question 4. We have a root tissue and we're going to place it in the open beaker. So here we draw the system and I have my root cell and I'm going to fill in my formulas because this is how I keep track of what's going on. Oops, sometimes they look like T's. All right, so the value for the water potential in the root tissue was found to be -3.3. So they're telling us this one right off the bat, and that's good to know. In the open beaker, the pressure potential is 0. So all we need to know is the solute potential. But again, that's the part where we need to know the solute potential. So -I CRT over here is negative, and this is sucrose, so it's going to be -1. I don't know what C is, right? That's the whole deal. Oh, do I know what C is? Yes, I do. It is 0.1 molar. And then we have our R, which is 0.0831. And then we have our T, which is 20 degrees Celsius, which would make it 293, right? And so we're going to do all this algebra, and this is going to equal -2.04 bars, right? So now I know that the solute potential is -2.4, and the overall water potential out here is -2.4, and it's -3.3 inside. And so the bigger number is the 2.4, and it's going to go from the solution into the cell. Question 5. Here is another one that's just kind of giving you this an example of what might happen, but we're going to do the same problem as last time, but now they've changed the solution to NaCl, right? And so already we know we have our cell with the water potential of -3.3, and we need to know the water or the solute potential out here, because we know that the pressure potential is 0 and all that good stuff, right? So here we set up our equation again, and this time it's -2 times 0.1 times 0.831 times 293. And so this is going to be the same math problem, but everything's doubled. So it's now going to be 4.8 bars, right? And so now it's out here, the potential is -4.8 bars. And this time that changes it so that there's much lower solute potential or water potential outside. And so the water is going to flow out, right? So by changing the solute from sucrose to sodium chloride, that makes the water move in a different direction, which is helpful to know. All right, and then we get to the next one. A plant cell with the solute potential of that has a constant volume when immersed in an open beaker solution. So here's a fancy way of saying we have our open beaker solution with our solute, our water potential formula here. And so now I fill in all the things that I need to know, and this one's gonna get crazy, so I'm gonna go back to using this. The plant cell has a solute potential of -7.5. -7.5, right? The beaker has a solute potential of -4, and we want to know what the pressure potential in the cell is. And so I keep filling out what I know, and I know that the pressure potential in the beaker is 0. So I know again that the overall water potential is -4 bars. Now, how do I relate these things? It says that the cell keeps constant volume, which would mean that the cell is in equilibrium. And so I know that overall, the water potential has to equal -4, right? And so -4 is equal to the pressure potential plus -7.5. And so this makes the pressure potential equal to 3.5 bars, right? And so now we have that, and that would make everything balance out. The next question, we have a cell, again, containing that much glucose is in equilibrium with the surrounding solution. It's in an open container. So I set up my problem once again with the basics. Oh, that looks like a T, even more than the other ones. All right, so this time I know my pressure potential out here is 0. The solution contains some amount of glucose, and the cell contains some amount of glucose. So I don't know anything else at the moment. I'm trying to find that. And so now I'm going to have to do some math. Let's start with the cell, because that's what it gave us, right? And so the solute is -I CRT in the cell. Oops, didn't put the negative. This is glucose, so it's going to be -1. The concentration is 0.6. We have our pressure constant, and then we have our temperature of 293. And so this is all going to come out to be -14.6 bars, right? And so now I know that, wrong place, that the cell is -14.6 for the solute potential. I need to do the same thing for the beaker. This time it's still -1 for glucose. We have a 0.5 molar solution. Can't do it. 0.831 times temperature. this one's all going to come out to be about negative 0.2 bars, 12.2 bars, negative 12.2, right? And so now we know that the solution has an overall water potential of negative 12.2. The cell is in equilibrium with that. And so the overall water potential in the cell also should be negative 12.2, which gives us another math problem of negative 12.2 is equal to the pressure potential plus the negative 14.6. Got to keep that negative in there. And so that would come out to be 2.4 bars, positive 2.4 bars, right? And so there you have that one. All right, and the last question, it's going to get a little crazy. We have our cell in the beaker. We have our formulas. Oh, I did that backwards, whatever. It's the same thing. We start filling in what we know. That is 0. We know that the cell has a pressure potential of 3 bars. But we need to know the solute potentials, and eventually we want to know the molar concentration, which is a little bit interesting. So we'll start with, let's see, the solute potential in the solution. The solution has sucrose, so it's -1. It has a 0.4 molar concentration, 0.831 times 293, and all of that is going to equal negative 9.7 bars, right? So negative 9.7 over here. The overall water potential is negative 9.7. Then we now know that since this is in equilibrium, that the overall water potential is also negative 9.7 in here. So we can actually just go right to some algebra on this one to figure out the solute potential overall, right? And so negative 9.7 is equal to 3 plus whatever the solute potential is. And so the solute potential is going to have to be negative 12.7. Now we're going to have to do some more algebra because the concentration, the solute concentration is somewhere in this number. And so now we know that negative 12.7 is equal to negative ICRT. Oh, that is not what I wanted to do at all. Oh, you're killing me, Smalls. Messed it all up. Hit the wrong button. Here we go. Is negative CRT. Ooh, different colors now. -1. We don't know C. We do know the other numbers. And so negative 12.7 is equal to negative 24.3 C. And so C then equals approximately 0.52, I believe. So 0.52 molar, and there's our final answer of the concentration of solute inside the cell. There you have it. Make sure to let me know if you have any questions. Hit me up on Google Hangouts or email, and good luck.